attending my it's my distinct honor, of course, to be with you. These are sad times, I think, for all Ukrainians, and my heart goes out to you. I'm shocked and at horror about what's happening in the Ukraine, and this is a very bad attack on your country, and I'm sad. And I think all conflict and all war basically come from the same misunderstanding, and that is sort of this belief: I'm separate from you, and you are behind that border, so you are inferior, and I am superior. And I think this is really a misunderstanding of our situation as humans. We are essentially all one. We have the same desires. We want to be at peace. We want to be healthy. We want to be with our friends and family. And I think the Ukrainians have the right, like everybody else on this planet, to defend that. And if you want, if you don't mind, it would be, I think, a nice idea to take just a minute or so of silence to honor those innocent people who have lost their lives, and also those who have, by acting for something greater than themselves, lost their lives. And that greater than themselves, of course, is freedom and peace. And so if you agree, let's just be silent for a few seconds, and then I will start with my talk. Because what I want to speak about today is actually something rather beautiful and something exciting and something I'm really enthusiastic about. And I don't want to make this contrast too sharp. So I'm fascinated, deeply fascinated with catalysis. And I think catalysis is one of the most beautiful cultural accomplishments of humanity in its history. I know this is a strong statement, and I'd like to convince you with my 30 minutes presentation today. And I would like to start out with what I would say is probably the single most important chemical reaction on the planet, maybe even in the universe, for us human beings, because photosynthesis, the conversion of carbon dioxide and water, which are normally sort of the end products of all chemistry, converts these materials into the stuff we eat, the carbohydrates, and the air we breathe, oxygen, right? So kind of the most important things for all life on this planet, at least for mammals like us. And this reaction happens in the leaves of plants. It's probably the only source of oxygen on the planet. And it requires light, of course, by the sun. But it is enabled by enzymes. And these are, of course, nature's catalysts, protein catalysts that accomplish this remarkable transformation. And as I said, the origin of probably all of mammal life on this planet. And it's also important to note that all of life would not be possible without catalysis. But there's more to catalysis. Actually, catalysis is a fascinating science. I would argue the most fascinating science. Of course, I'm somewhat biased. And it's the science of the catalysis of chemical reactions. For example, consider the reaction of A and B to C. Two compounds form a new compound, compound C. The catalyst enables this transformation, but it's used up in the process. And that is very important, because that means that a single molecule of a catalyst can actually create an enormous amount, trillions of new compounds without being used up. And that is why I like to call this principle catalysis a single molecule away from magic. This is as close as we can ever come to magic, I would argue. And it does so, of course, by lowering the activation energy of a chemical process. So that's the magic behind catalysis. So it's sort of the origin of all life. it is a fascinating science, but it is also a key technology. It is probably the single most important technology for humans on this planet, and it has been estimated to contribute to roughly 1/3 of the global domestic product. And it does so by ensuring that there is enough food on the planet to feed an ever-growing world population, to make sure to enable our health on this planet. We can make an example with catalysis. Of course, energy right now is probably one of the arguably single most important challenges for humanity. Transport, of course, what are we going to put in our cars in the future? And climate, the mother of all problems humanity is facing right now. And I'd like to show you now in the following few minutes 6 examples to illustrate this to you, in case you didn't know these reactions. 6 really, really important chemical reactions, catalytic chemical reactions that are really enabling our life on this planet. And I would like to start out with what is probably the second most important reaction after photosynthesis for our life. And that's actually already a chemical process, a chemical reaction conducted by chemists that utilizes an iron catalyst, and that's the Haber-Bosch-Process, in which basically nitrogen gas and hydrogen gas are united to form ammonia, again, catalytically. And this was discovered by Fritz Haber and Carl Bosch, and both have received a Nobel Prize for this discovery, because ammonia, of course, is a key compound to make fertilizers via the formation of HNO3. And from that, you can make nitrates. And just to give you sort of a feeling of the importance of this reaction, you can correlate the ammonia production over the years. This is from the 40s until 2007. Now we produce roughly, I think, greater than 150 million tons per year. With the growth of the world population, and roughly this is the sort of the same period, and you can see that probably only because of the ammonia that is produced with the Haber-Bosch process, there are now almost 8 billion people on this planet. Without ammonia, maybe there would be 1 or perhaps 2 billion, but certainly not 8 billion of us. In fact, a certain percentile of our body weight comes from synthetic nitrogen, which is incorporated, of course, into the amino acid and proteins in our body. So this was reaction number 1. Reaction also a bit biased because it was discovered at the institute where I am right now, the Max Planck Institute für Kohlenforschung in Mülheim an der Ruhr. This is in Western Germany. And that's the Ziegler-Natta-Polymerization, in which so-called Ziegler catalysts, which is a combination of titanium tetrachloride as a Lewis acid, for example, and aluminum organic compounds like triethyl aluminum, is used to catalyze the polymerization of small olefins, for example, propene, but also ethylene, of course. And this important reaction marked the beginning of what people have called the plastic age. Of course, you can think about it positively or negatively. Now the negative aspects are brought more into focus, but without any doubt, without plastic, we couldn't live on as we live right now. And roughly, I think 150 million tons of polyethylene and polypropylene are currently made annually with this process. And it has led to Carl Ziegler and Giulio Natta receiving a Nobel Prize in 1963. The third reaction is, in terms of scale, probably the most important catalytic reaction on the planet. It's done on almost a billion-ton scale, and that is the catalytic cracking of alkanes, which are obtained from crude oil. And those in the presence of a zeolite, it's sort of a mineral material, aluminum silicate at very high temperatures, can crack catalytically to give, this is actually a fragmentation reaction for the experts, to give alkenes and alkanes. And those are, of course, used as fuel to drive our cars and our planes, and unfortunately also our tanks, or yeah, depending on which side you are, of course. And in fact, people have estimated that this reaction is done at close to 1.5 million cubic meters of this feedstock per day. So roughly 500, almost like, yeah, greater than 500 million tons annually are produced with this process. And reaction number 4, this is also an alkane synthesis, quite remarkably, again, discovered at my institute, actually 100 years ago, the so-called Fischer-Tropsch-Process. It's actually an elegant way to make also fuels in case you don't have enough oil available. And Germany at the time, this is 100 years ago, was not in a good access position for oil. So they had to make the alkanes themselves. Actually, unfortunately, also to feed the tanks to attack the countries around us. But the way the chemistry is quite fascinating. It works actually by hydrating coal first. So the reaction of coal, which is abundantly available in my region and still is available actually, converting this into what is called synthesis gas. This is a mixture of carbon monoxide and hydrogen. And you can then react this mixture, synthesis gas, in the presence of heterogeneous metal-based catalysts, cobalt, iron, ruthenium, or nickel, into alkanes, all sorts of different chain lengths. And then you can distill out smaller ones, alkanes, and then use them. This is actually the correct stoichiometry as fuel material. And in fact, again, discovered at my institute, Franz Fischer, he was the first director, actually my predecessor many years ago, and his student and later group leader, Hans Tropsch, discovered this process. And this is a plant in South Africa. South Africa also didn't have good access during apartheid times to oil. And so they also used this process to make fuel. And currently, this is still run, actually, quite interesting. It's not just an old reaction, but it's still possible to make fuel this way. And it's also actually an interesting alternative to make natural gas, methane, and so on. You can also use synthesis gas to make, even smaller alkanes. And perhaps this reaction will become more important in the future. And so when you then have made alkanes, either via Fischer-Tropsch or from catalytic cracking, what are we going to do with all this billion ton of fuels? Well, we fill our cars and then burn them. And stoichiometrically, actually, the reaction that occurs, in case you're interested, is shown here. The alkane, this is octane. This is kind of one tank, one loading for one car, roughly 50 kilograms, 71 liters, is reacted with oxygen from air. And you need 176 kilograms for that tank, for that amount of fuel. And this is converted into 155 kilograms of CO2 and also 71 kilograms of water. And so, but that's only the stoichiometry on paper or on this PowerPoint. But in reality, of course, unfortunately, it doesn't work that cleanly. And a lot of other stuff comes out of the exhaust, including sort of this coal stuff, but also alkanes resulting from incomplete combustion, but also NOx compounds. These are toxic and potentially cancerogenic. These are formed in any combustion when there's air available, because the nitrogen also gets oxidized in the process. And of course, also from incomplete combustion, carbon monoxide is formed. And so for this, people have developed yet another catalyst, the so-called three-way catalyst. And this consists of a mixture of, again, metals, fine metals, platinum, rhodium, and palladium, which are dispersed on aluminum oxide. So you have a heterogeneous material. And these three different types of catalysts enable these three transformations: the complete oxidation of carbon monoxide, the complete oxidation of alkanes, and of course also the conversion of NO into N2 plus CO2. So in this reaction, actually both NO and CO is converted into less toxic material. So that's the most commonly known catalyst in Germany. It's just called the catalyst because everybody knows it from the car, of course. And last but not least, the last reaction I wanted to share with you, or the last type of reaction, actually is asymmetric catalysis. And this is important when you want to make molecules that behave like object and mirror image. And many molecules actually behave like this, and this is important, especially when it comes to pharmaceuticals. Then the body actually, for a still unknown reason, can differentiate between these energetically identical molecules. And it prefers to interact with one of them whereas the other one might be toxic or ineffective. So the synthesis, the selective synthesis of these mirror image molecules is very important. And for that, people have developed asymmetric catalysis, where we now use catalysts that have that handedness already in them. And this is one example of a rhodium-based, a metal-based catalyst with a chiral, what is called a chiral ligand, a diphosphine, which coordinates to it, and then you can hydrogenate an olefin to give these amino acid precursors to make, for example, L-DOPA. And this is an important pharmaceutical against Parkinson's disease, which has been made, maybe still is being made using this process. And this, again, by the way, has led to a Nobel Prize actually in 2001 to William Norrells, Rio Nuyori, and Barry Sharpless. I have just met him actually earlier this month in San Diego at a conference, and he's still an incredible and inspiration for many people, including myself. So the one thing you should have noted actually is that in all of these 6 examples that I've given you, metals were the key elements of the catalysis. And this is also reflected actually in all the Nobel Prizes that have been given to the general area of catalysis. If you look at it, starting with Oswald, who basically laid the foundation, the physical, organic, or physical chemical foundation for catalysis, and following up with many, many other Nobel Prize winners, I think there was maybe 17 or so over the last century. All of these prizes were given to chemists utilizing metals as catalysts, either heterogeneous catalysts or homogeneous catalysts as metals. But all of these Nobel Prizes were given to research on metal-based catalysis. The other Nobel Prizes that were given to catalysis researchers were given to enzymes, of course. And I've mentioned both to you. Enzymes, of course, are important for life and for photosynthesis. And these metals are important in all the chemical reactions I have just shown you. And so this actually was sort of the chemist view in the late 20th century. We were all kind of convinced that when it comes to mirror image selective catalysis, or asymmetric catalysis at least, you only have these 2 options. You can either use enzymes or you can use transition metal complexes to catalyze an asymmetric reaction. So that was the state of the art, and that was what we were all kind of convinced. And in that spirit, actually, I decided I want to work with enzymes. And so I moved to the Scripps Research Institute, and I worked with a very special class of enzymes, so-called catalytic antibodies. Antibodies are normally not catalysts, but you can train them or you can select them as enzymes, and then they are actually catalysts. And I work with one catalytic antibody, a very peculiar one, that catalyzed the so-called aldol reaction. It's a reaction between 2 carbonyl compounds giving so-called aldol products, a ketone and an aldehyde. And my task then at the time, as a postdoc actually initially, was to figure out the mechanism of how this antibody catalyst, how this enzyme works. And what I realized was kind of surprising to me actually, because I found that in the active site of this protein, there was no metal. All there was an amino group and an acid group. And with that, that's actually sufficient to catalyze this very challenging transformation by first forming an iminium ion of the ketone, which can then be deprotonated to the enamine, and the enamine then reacts with an aldehyde to give the iminium of an aldol, and after hydrolysis, the aldol to regenerate the catalyst. So this is actually what I found out, how this catalytic antibody works. And this is also the mechanism of natural enzymes that catalyze the same transformation. And so then my thinking went on. Later, I became an assistant professor at Scripps. And I thought about this, like, why is it actually that we chemists are so in love with metal-based catalysts when nature actually is much less biased? There are, and of course, enzymes that use metals in the active sites, but there are at least an equal amount of enzymes that are completely metal-free. And so I started to wonder, maybe it's also possible to use small organic molecules as catalysts for asymmetric synthesis. And I thought about it for a while. So you need an amino group, you need an acid group. Why not using an amino acid And that, of course, came after first, designing different catalysts that have an amino group and an acid group. But I remembered, of course, proline, the amino acid proline, this is an edible molecule we produce in our own bodies. It's non-toxic, of course. It's a so-called non-essential amino acid because we make it ourselves. We don't even need it from food. Proline had been used in the late 60s as a catalyst, but people have not understood how it works and how it worked. And that is probably why this chemistry was not really followed up upon. And I found then that indeed proline that has everything that is needed, an amino group and an acid, catalyzes aldol reactions as well. And you can convert acetone and isobutyraldehyde, for example, into the desired product in state of the art. I should say, defining the state of the art in antiselectivities of 98 to 2. And this was also true for many other substrates and led actually to this very first paper of my group, actually back in 2000. And I have to say, maybe until today, I think the most important paper that I've published so far. And ultimately, it has helped, I would argue, or has encouraged other people to work with small organic molecules and has helped in sort of complementary work of Professor Macmillan to shape up the field of asymmetric organocatalysis, for which I have just received the Nobel Prize actually last December. So over the years, we have actually used this principle a lot, and hundreds of papers came out later by other groups as well on utilizing this what we have called aminocatalysis, the catalysis of this amino group, right? But there is more to proline. Actually, it's a bifunctional catalyst. I think I have already indicated this. It also has this acid functionality, which is very important in each of the steps of the catalytic cycle. And more I realized actually that this is actually even more important than aminocatalysis, acid catalysis. And I came actually to conclude that acid catalysis is probably the single most general type of catalysis there is. And in fact, the majority of all reactions that you can catalyze in principle can be catalyzed by acids. And we can discuss this later if we have experts. Maybe you have a different opinion about this, but I have a good substantive reasoning for this argument also. And that is all that actually acids need to catalyze a chemical reaction is a certain amount of electron density in the substrate. And now a little challenge for you, think about chemicals that are devoid of electrons. And then you will realize that very, very few chemicals, in fact, I think it's only the proton probably that is actually free of any electrons as a chemical. So basically, as a minimal requirement for acid catalysis to occur, what is needed is electron density. And so we have focused on this over the years, and we had what I would call a big breakthrough recently, and that was actually the discovery of a new type of strong, very strong Bronsted acids. And Bronsted acids that are not only strong, but they are also what we call confined. And that is, they shape up an active site, very much like an enzyme, a well-defined active site in which substrates are sort of bound in a lock and key principle, which enables several very unusual transformations. I think we have collected since this discovery in 2016, maybe up to 20 or so distinct chemical reactions for which there are no other catalysts that accomplish this kind of reactivity. And I would like to just share with you a couple of them. Reaction number one is an aldol reaction, also a so-called Mukayama aldol reaction, in which you use these ketene acetals reacting with ketones as the electrophile. And these reactions can be done on a multi-gram scale with only tiny amounts of the catalyst. In fact, in this paper, we report one example where we use a catalyst loading that is lower than 1 part per million, which to my understanding, to my knowledge, is the lowest catalyst loading that has ever been used in any small molecule catalyzed asymmetric carbon-carbon bond forming reaction. Perhaps even for enzymes, I'm not sure about this. I would imagine that enzymes are more reactive, but I'm not aware, at least, of examples with such low catalyst loadings on a preparative scale, of course. This is the reaction number 1. And reaction number 2 was just published very recently in Nature with Dr. Hui Zhou, an amazing postdoc from China. And she has discovered a hydrocyanation, or to be precise, a sinyl cyanation of ketones, actually, that is also catalyzed by the same confined and strong acid catalyst class. We call them ID-pi catalysts, actually. And you might now wonder, why is that important? Because there are many, many different sinyl cyanation and hydrocyanation catalysts in the literature. In fact, it is important because of that fact, because this specific reaction can be catalyzed by enzymes, it can be catalyzed by transition matter catalysts, and it can also be catalyzed by organocatalysts and very sophisticated ones. But it turns out that none of these previously developed catalyst classes, and there are really dozens, can catalyze the enantioselective addition of cyanide to 2-butanol, which is kind of one of the smallest of a ketone that can be enantiodifferentiated to give this product here. And even engineered enzymes actually give lower enantioselectivity in this specific case. So we were kind of proud because this product is also useful intermediate in the technical synthesis of a couple of pharmaceuticals that are on the market. And so last but not least, I would like to sort of point toward the future. So this was all kind of chemistry from the past and from the current time. And I would like to encourage you, if you're interested in working on catalysis, to think about more sort of sophisticated reactions. And the ultimate dream reaction of mine is actually shown on this PowerPoint here. And that would be the conversion of CO2 to carbon and oxygen, kind of the essence of photosynthesis. And try to find in the literature, if there's one example, I'm not aware of one. I'm not even aware that people have proposed this transformation. But I would like to encourage you to think about it. Can we use UV light from the sun and design catalysts to enable such a transformation? Perhaps the direct transformation, converting really CO2 from air into carbon and oxygen, but also variants of that. For example, we can use plant waste, and I think there's plenty of plant waste produced on the planet right now. And typically plant waste is rotting, and then CO2 is generated again in the process. But if we would take the plant waste and I've heard from colleagues here at the Institute, would just dig it under the earth, it would be also converted back to coal again. And that would then sort of be, in essence, the same process that I have shown you here. So think about it, and also think about potentially doing this directly, converting CO2 back into coal. This is where it all came from. And I would like to discover something like this. It would give the silly name of my institute, the Max Planck Institute for Kohlenforschung, a new meaning. In the past, we have used coal to make gasoline, and now we can use maybe CO2 to make coal, kind of reverting what humankind has done in the last century or so. And I think it's a worthwhile goal for all of us, and I hope I have encouraged you a little bit with this presentation. Last but not least, I would like to thank my co-workers. You can see these people here. This is actually on October 6th when the Nobel Prize was announced, and you can see many, many happy faces from all over the world. And I think this somehow goes back to what I said in the beginning. We are all one, right? We are all the same. We all share the same passions, the same desire for peace and for our health and for our safety. And you can see people from Kyrgyzstan in my group, from a few from Germany, from Catalonia, from India, from Italy, from the United States, from China, of course, from Japan, from all over the world. Even there's one guy you can see here. This is actually Oleg Grossman. He has just graduated as a PhD student and is now working for BASF. He's from the Ukraine. And I have currently a master student, Katarina Krivos. She's also an amazing co-worker from the Ukraine. And you can see we're all happy in this laboratory. We share this excitement for our work. We're very enthusiastic people. And I hope with that I can share some of the enthusiasm that we have in my group. I wanted to also show you our campus. This is Mülheim an der Ruhr. This is the city where we are. It's kind of a small town. I'm kind of happy and that we are in peace right now. It's a very peaceful town. There's this river Ruhr. You can swim in it. It's relatively clean. This is our campus here. This is where I am right now. Actually, this is exactly where I am. At this window here in the top floor of this building, I have a great view. This is, by the way, where I live. So I have a 1-minute commute to the institute, and we're very, very happy here. And if you're interested, and if you're a chemist, and if you want to visit us, I'm more than happy to invite you spending some time with us. So thank you very much for having me, and all the best for all of you. God bless you.
Thank you. Thank you very much for a great lecture. It was a big pleasure for us to be with you today and to hear you. It's very important for us right now, this support, what you did. Well, we have some questions from our participants. The first one is, what is the role of catalysis in medicine?
Sorry, what is the role of catalysis
in medicine?
Yeah, something people are not so aware of, but pharmaceuticals are chemical molecules, right? And these are typically small organic molecules, and they are made and designed typically by chemists, right? We always give credit to the doctors of the world, and rightfully so. They heal us, but they use actually chemicals. And these chemicals are made frequently using catalysis. For example, there are antiviral drugs on the market right now, which are made using organocatalysis, and they heal people actually, or at least they prevent the disease from happening. So there is a role also of catalysis for medicine. You know, many of the drugs we're using would not be available without catalysts.
All right, the second one. Does the blue molecule differ due to the mirror reflection?
Excuse me, can you repeat this question?
Of course. Does the blue molecule differ due to the mirror reflection?
Maybe there's a misunderstanding here. So there are molecules. Molecules are three-dimensional objects, right? So, for example, this is the molecule proline, the amino acid we used as a catalyst, and you can see it's kind of an object, a three-dimensional object, and some have this property that the mirror image actually is not superimposable with the object. And that means there are different molecules, basically like our two hands, the right hand and the left hand. These are different objects. They behave like object and mirror. And if you would see just the hand, you would still know it's a right hand or it's a left hand. And so they have different properties in our bodies. And that's why it's important to be able to make them selectively, right? And that's because that's a feature of many, many drugs, that they have what is called this chirality. And that's the point I wanted to make.
Okay, do you know something about the catalysis on the surface of water? What the extent of this process study, and what are the prospects of researching this process?
Catalysis on the surface of what?
Water.
I'm sorry, but I cannot really say anything about this. I don't really know what you're heading at, but there are surface effects. Water has a special property. It has this surface tension because it has this intermolecular aggregation. Normally, molecules of that molecular weight are gases, right? It's one of the smallest liquid, actually, and that's because of it has strong bonds that hold it together, and that's why it's a liquid at room temperature. And it has also what is called a high surface tension. And there are effects I've heard about, but I'm not an expert in this area, so I cannot really contribute.
All right. What are you working on right now? Like, do you have any other project that you?
Yeah. Yeah. So basically, my lab, we are doing fundamental research, right? We have this luxury that we can work on things that are not normally needed or useful for society. We can basically research whatever we want here. It's kind of the freedom that we have in the Max Planck Society and in academia in general, I hope, in Germany. And so most of the stuff we have done was very fundamental, like the questions like, can we catalyze chemical reaction with organic molecules is one of those. But right now, perhaps inspired by the crisis on the planet, we also think, how can we use our intelligence, our creativity to mitigate problems on the globe, right? For example, during pandemics, we tried to make an antiviral molecule, remdesivir, and we have been successful in developing a much shorter route to this drug. In the meantime, of course, there are vaccines, and the drug is still used, but maybe sort of less so, and there's also the supply is sufficient of this compound. But we have developed a very elegant and very short route to remdesivir. But for currently and for future studies, I would really like to help in solving sort of the sustainability problem that we're facing right now. And there are two ends how you can work on this. One end would be to use our fossil materials, hydrocarbons and coal, in a more efficient way, rather than just cracking them and then burning them in our cars. I would like to develop sophisticated catalysts that convert them into much more valuable materials. For example, pharmaceutical precursors. This would be something that we are really fascinated with. And the catalyst class I have shown you in the end of my presentation, that the ID-Pi catalysts are very reactive and yet very selective at the same time. And with those, we hope to be able to activate hydrocarbons, arenes, alkenes, and alkanes. So this is the one direction. But the other direction, of course, is that we actually start to build up a chemistry from CO2, right? Because at some point, I hope it's not happening so soon, and if we spend our fossil material in a more sustainable way, we can keep it for a few hundred years, right? But at one point, it will be gone. And then we have to start with CO2. And we have to do this in a more efficient way and in a really scalable way. And that's why I think about processes like the one I've shown you in the end. Can we convert CO2 into C again? For example, into, coal or even diamond. Why not, right? It would be kind of beautiful. And it is thermodynamically possible with UV light. Of course, it's a chemical uphill reaction. And it will be really challenging then to separate C from O2 because otherwise it burns. But I think it's kind of sort of a creativity platform toward future challenges. And as a chemist, I cannot think of any reaction that would be more important for our life on this planet right now than actually converting CO2 into material that is either useful or disposable on a billion-ton scale.
All right. Thank you. What inspired you to become a scientist? Like from this from the school, maybe it was in the school or something.
Oh,
I mean, when you started, it was but this interest becoming increasing, and you wanted to become a scientist.
So in my case, actually, it was philosophical interest, and I wanted to understand the world, and I wanted to, most importantly, I wanted to understand humans. Why are they like they are? Why do we behave like we behave? And I knew somehow, or I was told, that the world is made of atoms and molecules, and I've heard that chemists are the ones that deal with atoms and molecules and understand how they interact. And so I thought, if I study chemistry, I understand everything. I understand why we are like we are. Of course, later I found out that's unfortunately not the case. You can study as much as you want chemistry. You will not figure out human behavior from that. And you will also not understand sort of the big questions, the philosophical questions. Why is there a universe and not nothing? Why are we here? Where are we coming from? Where are we going? All these things, unfortunately, chemistry cannot answer. But when I realized this, it was too late. I realized you can make, gunpowder with it and other fun stuff. And I was kind of hooked. And so it didn't leave me. And until today, I really enjoy chemistry and science as a whole. I mean, science is beautiful because we discover something new every day that nobody has seen before, right? And that's true for physics, for biology, and for chemistry. But chemistry has this special additional feature, and that is, it is a synthetic science, right? So we can create our own objects. Now think about it, if you're an astrophysicist, You cannot create a supernova or a star or a galaxy and clash two neutron stars. There is no way you can do experiments. You can just observe, right? And that's the beauty. Chemistry also captures creativity. So it's the scientific spirit and the creative spirit that comes together. And that's why I feel so much at home. But I can encourage all of you to think about, if you have this inclination towards science, go for it. It's a very, very rewarding place to be, I would say.
What do you recommend for the young scientist students to, like, few tips and few recommendations on this big, hard way to become a scientist?
Yeah. My most important recommendation for all of you, and this not only applies for scientists, but for everybody. This is what I tell my kids. This is what I tell anybody who's asking, what shall I do with my life? I would strongly advise you to follow your enthusiasm. And that means do what you really love to do. And if you're good at it, this is the best thing that can happen to you. Like in my case, for example, this is my hobby. This is my passion. Science and chemistry, right? So I never felt like work, right? Of course, sometimes I have to go to meetings and I'm maybe not so excited about, but the majority of my time I spent in enthusiasm. Like this whole day, for example, we work on a reaction I'm really fascinated with, and I get news from my graduate students. They come in. This is so much fun, And so my recommendation is follow your enthusiasm, because if you set yourself a goal, for example, I want to be rich. And how do I become rich? Maybe I should be a finance guy and I should work on the stock market. Then you may or you may not end up rich, but you will certainly do something that not necessarily is what you love to do, right? And then it feels like work, right? Whereas if you do what makes you happy, then you might or you might not achieve your goal. For example, winning a Nobel Prize or not. But at least to be honest, I couldn't care less. What I do, I love to do. And with the Nobel Prize, of course, it's even better and it's very exciting. Don't get me wrong. But it was already exciting before and very, very satisfying. So think about this. This is really important. Don't listen to what anybody else tells you. Don't listen to me. Follow your own enthusiasm. That's my recommendation.
Thank you. Thank you very much. That was a great time. Thank you for your support and for the great lecture and great tips for our students. I guess that very soon there will be a peace in our country, and probably we will meet in person in Kiev. There's a great lecture in a big auditorium.
I would love to come, and you're, as I said, you're all welcome to visit us if that's possible. And I wish you well. Stay safe.
And I'm really excited, to invite you to our science museum that we made with our students. That's amazing. Thank you. Thank you so much. It was a pleasure to talking to you. Thank you. Have a good day. Bye. Bye-bye. Thank you.